This video talks about how to estimate a GARCH MS model. In this video, I do assume that you are familiar with the estimation of an ArchM model, and ideally that you are familiar with the notation and concepts that I've covered in my video about estimating ArchM models. So we start with the basic return decomposition, where realized returns in T equal the predictable part mu t minus 1 plus the return shock epsilon t. And epsilon t is just equivalent to sigma t minus 1 times times the white noise shock eta t. Now, the GARCH MS parameterization assumes that this conditional variance sigma square t minus 1 can be written as follows. So you see, it is linear in the past m squared return innovations, and it's also linear in the past s variance terms. Now, there are some parameter restrictions. First, alpha 0 needs to be positive. All of the alphas need to be 0 or positive. All of the beta need to be 0 or positive. And there's this restriction that the sum of alpha I, beta I, sum going from I to 1 to the max of m or s, that needs to be smaller than 1. As an exercise, I would invite you to verify that the unconditional variance of a GARCH MS process looks as follows. For that verification, you have to use the stationarity result that we've used quite often when determining unconditional moments for the arch processes, especially for the arch 1. That's what we have shown in the previous video. So, now as with the arch processes, one can estimate the parameters of a GARCH MS model with maximum likelihood. For didactical purpose, I do mimic the ARMA PQ ArchM example from the video on estimating ArchM models. In doing so, I assume that we want to fit an ARMA PQ GARCH MS model to a time series of monthly S&P 500 returns. So the resulting parametric model for monthly S&P 500 returns reads as follows. The realized return has that ARMA PQ structure plus return innovation epsilon t, and here right away I assume that the epsilon t follows a Gauss distribution with mean 0 and variance sigma square t minus 1. So these returns are conditionally Gauss with a time varying variance, so the unconditional distribution won't be Gauss. Now sigma square t minus 1 follows that GARCH MS parameterization. Instead of slicing the estimation problem into several subproblems, as I have done in the video on estimating ArchM models, I will here only write down the joint log likelihood function, which you then have to numerically optimize. So the joint log likelihood function coincides with that familiar expression. The only thing new is that the sum starts at t equals 1 plus the max of PQMS. Otherwise it has the same known three components, minus half log 2 pi, minus half log sigma square t minus 1, and then minus half the prediction error to the power of 2 at time t divided by the conditional variance. Now the prediction error is defined as follows. You see, it's just the realized return minus the ARMA PQ parameterization, which also shows you that you can identify these parameters based on that likelihood. And the parameterization of the variance is that GARCH MS parameterization, which also highlights you can identify the alpha i's and the beta j's using that log likelihood function. And then we have that the sigma square 0 is given here by the unconditional GARCH MS variance. Now you have the log likelihood function. You could program that up, use your optimization routine, and find the parameters.
Got feedback? We would love to hear it. Please drop us a line. And if you liked the video, give it a thumbs up. And don't forget to subscribe to the channel.